with Irene and André. Irene is an electronics engineer and she's an expert in FPGA-based electronics and signal processing. She joined CERN's BIM instrumentation group in 2016, and she's currently developing the RF SoC data acquisition for BIM position monitors, and she's coordinating the SoC Framework Project, as we will see. And André is a digital electronics engineer. He joined CERN's Power Converters group in 2023, contributing to the gateware of the function generator controllers. And today he works on the DIoT project, as we will see. He's contributing across gateware, low-level software, build systems, and general support.
Okay, can you hear me clearly? Maybe not yet. Wait. Yes. Don't put it there because it falls. Thank you. All good? Yes? Thanks. Okay, so hi everyone. Irene. So indeed, today me and André are going to talk about how we are standardizing SoC development in CERN's Accelerator complex. And in particular, the technical focus will be on the build system for Xilinx Platforms. So indeed, there will be two parts to this talk. The first part, which is my part, is about this ATS system-on-chip framework. So I will give a brief introduction to the topic. And then I will give you an overview about how system-on-chips are used in the CERN's Accelerator complex and what are the common use cases, common issues. And then based on this, I will present to you the ATS system-on-chip framework projects, which is building a standard framework to use SoCs in the accelerator. Then in the second part, by André, you will see one component of this framework, which is the DIoT build system. So we'll give you a motivation for this development, an overview of the features, then a closer look to some of these features, and then guidelines about how to use it. So let's start with an introduction, which is mainly a list of acronyms and their clarification, which since there are indeed many. So first of all, system on chip. So here we are indeed kind of all familiar, but it's good to clarify that in this case, we are defining SoCs as integrated circuits containing a CPU, so an hard CPU, with a multiprocessor, so, which can be a multiprocessor system, memory interfaces, input-output devices, interfaces, and FPGA-like programmable logic. Then, just to give you a clear example, so I've heard it already from many talks, so we all mostly familiar with the Zinc Ultrascale Plus multiprocessor system on chip, in which we have a processing system with different processing units, a programmable logic, which is interfaced through an integrated bus and high-speed ports, and then FPGA fabric logic in it, and then on both of them we find connectivity and then memory interfaces. And then all of this is integrated in a single device. Now, in CERN, we will look at example of hardware using a system on chip. One example is the DIoT, so the distributed IoT framework, which is a modular electronics platform developed by the CEM group in the BIMS department. So it comes with a RAD-free and RAD-tolerant version, and is based on a compact PCI serial 3U crate, and is used as a foundation for a group of CERN projects. So it's a platform that is used by different projects. And why is it interesting in this case? Because in the crate, we have a system board, which is using a Xilinx Zinc Ultrascale Plus multiprocessor system on chip. And as part of the platform, the project also provides tools, libraries, and OS for this platform. Then also I've already mentioned the ATS sector, so probably you remember from the presentation of Eva. So at CERN we have different sectors, and one is the Accelerator and Technology sector. So in this you find different groups, and all of them, they cover a big variety of electronics and software systems that are integrated in the same accelerator control infrastructure. So just in the presentation before, you saw an example of 2 systems from one of these groups. And then there is, in the BEAMS department, the control groups, so CM and CSS, who provide also central services and support to the equipment groups that develop and support all these other systems. Then another acronym that you're going to hear is the FEC, so we call FEC a front-end computer. So there is a set of FECs that are officially supported by our BEAMS department, and for these we are obliged to use a standard Linux operating system. So the old one was CERN CentOS 7, and now we are moving to a new version of it with the FEC OS. And then another common acronym is FESA. So FESA is the front-end software architecture that defines the standard software classes that we use on FECs. So maybe others are familiar with EPICS, for example, which is another standard software framework. In the accelerator at CERN, we use FESA. And then another one is TN. The TN is the technical network. So indeed, is this TN network in which the FECs are integrated and through which they talk, and they're integrated in the accelerator control system. So indeed, how system on chips are used in CERN Accelerator. So we did a survey in 2023 in which we started gathering all information about systems at CERN. So here you find a list of all the projects that came out from this survey, so including R&D project, first developments, but also some early adopters of the technology. So SoCs were not yet extremely distributed among the accelerator, but they are appearing. So you see several groups, and you see several projects, and then when we go looking more at the numbers of components, we see through the future until the long shutdown 4, that we are going to count up to 3,500 system on chips and more, and then how they can be distributed among different groups, among different departments. So many different people working on this platform across the accelerator. Then another interesting fact, what we found out is that among all the projects we interviewed, is that all projects are using AMD Xilinx system on chips. And then when we look at the family, most of the projects are using UltraScale Plus multiprocessor system on chip. We have a couple of previous early adopters that are using the Zinc 7000, as you heard also from the ABT group in the previous presentation. And then one example of project using the RF system on chip, which is actually me. And the interesting fact from this is that so if we count the new development, all the systems share the same processing system cores. So we can standardize on the UltraScale Plus multiprocessor system on chip family. Then the other questions were regarding what are common needs, what are the technical challenges for these projects. And indeed, one of the things were how to build your project in a standard way, how to keep your repo, how to integrate a CI for a system on chip project. Then how to boot your system, and how to boot it from the network when you use it in the accelerator infrastructure. How can we share IPs? How can we maintain, where do we get our OS, and how do we maintain it on the long term? But also, if we put our SoC on the network, how can we remotely reset it, or how can we have a remote console to access our SoC? And then other things like how can we propagate system monitorings and diagnostics if there are any ready-made solutions. And then something that is very specific to the accelerator is I have a SoC, I have a standard network with software that I have to interface it with. How do you do it? What should we do in such a way that we don't do many different things at the same time? So indeed, is one of the big topics, and there were two main solutions identified. So the first is to use a SoC as we are using currently FPGAs in general. So as an hardware module, we don't want to have an OS on it, and we integrate it through an external front-end computer. And then most cases here are using like micro-TCA platforms or anyway PCI Express interfaces through it. The other possibility that came up is I have a SoC with a multiprocessor system. Can I use it directly as a front-end computer in my network? So there the interest was into just adopting all our software stack, standardized software stack for standard front-end computers directly on the system on chip. So indeed, to get together with this, the OS supported centrally, the registration in the databases, the running the same software framework, using the same network protocols, so CMW and RDA, and then have the same way of having system logs propagated, diagnostics propagated, but also receiving the machine timing and so on. So indeed, on this baseline, the project was born, and we are now in development. So now it's just a brief list of the things that are going to be there, and then we'll go to the details from André on one specific task. So indeed, the project has been split in several work units that are managed by the several aspects on all of these parts. So one work unit is on the system on chip based project, and this is strictly related with the IoT project, which is already a common platform. So indeed, here we find the build system scripts, which are going to be presented by André later, but also a solution for booting with a fail-safe image, the device tree generation, scripts and tools for propagating updates of hardware and software, and also libraries for the propagation up to the software of custom sensor and diagnostics measurements. Then another work unit is a system on chip platform control. So also here it's correlated with the IoT project, but is taken care of in the BIM instrumentation group. So one of the highlights of this activity is the development of remote power cycle and console. And currently we have a prototype implementation in the PMU firmware. So we are using the platform management unit of the SoC to get to the network independently from what is running on the APU, a remote console and the possibility to remote reset the core. And then in the work unit 3, this is very accelerator related, so the fact of using the front-end software, so the FESA, on the SoC, and to receive timing. So indeed, an interesting development here was the development of this timing front-end library for reception of events with less accuracy than when having a timing reception hardware card, but still it's possible to receive timing events through the network. And then the one big part is indeed the OS and the sysadmin part, which was indeed a big scratch heads for all the early adopters of this technology. And one of the goals of the project is to provide a distribution image, so a distribution of a centrally managed OS to all the systems. And in this case, we want to have the same FEC OS that is provided to the other standard front-end computer, but with the kernel that is the Xilinx Linux kernel. And then for this also to have the standard boot sequence from the network, to have the extension of the database, to cover also system on chips, to have syslogs, to integrate this with our platform for diagnostics, which is Cosmos. So the idea is to not invent new tools for SoCs, but to try to reuse everything that we already have. So indeed, I leave the floor to you. Yes, you do. Perfect. Yes, you do.
So thank you very much, Irene, for this very insightful review of the SoC workforce program. I would like to bring the attention back to one of the parts of this big workforce, which is the IoT project, which correctly so, Irene told you guys that it's a modular platform that allows its users to develop its own custom electronics, while basing it in a solid, already built and tested framework of electronics, of mechanics, of a system board that already has a SoC, of a firmware, bootloaders, and of course, a build system. Doing build systems is normally a very interesting exercise, and more so if you're dealing with a project that has to be extended, like the DIoT. So while building a build system for this project, you cannot only focus on the requirements of the platform itself, you also have to focus in the modularity and expandability of the project, because that's paramount for the users to add their own logic and their own files and implementation over it. So it has to be modular, it has to be complete, but also this cannot be an excuse to make this system bloat, because if you start to add a lot of features or want to incorporate a lot of tools, you end up with a monster. So also one of the requirements is keep the system very simple. Because, as we all know, when we deal with digital hardware, FPGAs, or all of these kinds of systems, we are normally working with vendors and with tools that generate files, and you're dealing with binary blobs, you're dealing with files that inherently are not good for version control or for a classical build system. So we have other concerns that you have to be in mind. For example, a classical example is a block design. If you have a block design and you want to add something, an IP, if you generate the file that it stores, it can have thousands of lines of difference, so you cannot really use it as a way to keep your files in a repository. So with all these requirements in mind, we built a build system, and here are the main features that we implemented in it. So first of all, it's a complete build system for Xilinx SoC, both for firmware and gateware. So you can build all of these, I'm not going to read the list, all of these sub-projects, and generate a bootable boot pin that is complete and is going to grant you a system that can be put in operation. To make it simple again, we only use easy tools that are already normally present in normal operating systems like Linux, which is GNU Make and Bash. And of course, we are dealing with Xilinx, with Vivado, so we are using Tcl to interface with the IDE. You can expect the classical recipes. And of course, like normal build systems, it's incremental, and the build system is capable of realizing if only part of it is out of date, and only really re-implement these parts of the whole solution. The system, once again, has to be modular and is easy to expand. For this, we devised two systems. We created a patching system for all of these sub-projects, for example, for the gateware or for the U-boot. And we also created hooks, so entry points for the user to modify the reference design to their own needs. We also implemented a tempering system, which I'm going to talk ahead, and it's a multi-project solution. So, for example, for the different versions of the system board, we can all have them in the same repository, and the build system will be able to deal with it. Last but not least, we also exploit the functionalities of CI for FPGA. We're not going to talk too much about it, because right after this, we're going to have a presentation by Christos on this system. But essentially, in a nutshell, it's a collection of pipeline runners, so for CI, and it's also a collection of containers, of Docker containers that already contain all the tools needed to build these projects. And of course, we provide already a pipeline, so it's easier for the users to implement their own stuff. So let's have a closer look into some of the features that I find interesting in the build system. So for example, for gateware compilation, we have a mixed solution between make system and Tcl, because if you want to make a traditional make solution and you want to build your project in the incremental fashion, so okay, you have to create a project, you have to build the block design, you have to synthesize, you have to implement, and you have to generate XSA. If you have a rule for each one of them and you call Vivado, you're going to have a lot of overhead, because Vivado has to open the projects, and it has to close. All of these grants a significant, I don't know why, overhead. So what we did is use the mixture. So we leveraged the dependency graph resolution of make files, and we call only the recipes or the rules that need to be created or updated. So here you can see, let me see if I can use a pointer. On the left, this picture, I just created the block design, and I tried to call it again, and the prompt exits immediately because the project was already created, so there's no need to redo it. Right after that, you can see on the right, I asked the make system to build me the implementation of the gateware, and of course, it was not done before, so it has to be done. But you can see here in the build options, It says synth and implementation. So it knows already that it doesn't need to create a block design again, it doesn't need to create a project. So it goes straight to the point. Another very cool feature of our build system for the gateware is the visibility of problems. So if you've tried to compile your gateware through a command line, you notice that there's a lot of logging. And the important messages like critical errors, critical warnings and errors, and even normal warnings, get washed up into the background. So it can be easy to miss mistakes. So what we do is, right before we exit back to the terminal, we print out again in red all of the critical warnings and errors, so the user can know exactly if there's a problem or not with their design. We also make sure that if the design doesn't meet timing requirements, the project will fail by design. This is especially useful if you're dealing with a pipeline, a CI/CD pipeline, which in any case will give you a boot image. If you're not scrolling around the logs, you'll never know that you don't have a timing closure. So this makes sure that the user knows what's happening. And finally, another cool feature is the user might modify our files and essentially, modify the files that are used to create the project, and not by mistake forgot to generate the project. The base system is again capable of identifying this, and right after calling for a compilation, it prints in yellow that these sources are not up to date. So if you want them to have effect on the project, you have to regenerate the project. So about expansion and modularity, I told you already that we have two systems. You have the entry points and you have a patching system. So for each one of the sub-projects that need some kind of expansion, we have one of these systems. So the patching system is mostly for us, for the platform, because we have to deal with our own hardware on the system board. So for example, enabling a PHY chip or programming a PLL of SI Labs clock chip. But for the user, we have also, of course, points for them to add their own logic and their own files to the, for example, to the gateware. And you see that through the project config tickle and the user BD tickle. So in the project config tickle, the user can add IPs, can add VHDL, any kind of sources. And in the user BD, it can modify our reference design and add their own IPs. The same thing happens to device tree. In device tree, you have also two entry points, one for the programmable logic and one for the processing system. So the user has full flexibility to implement their own logic into our solution. And for the patching system, it's interesting to also note that, of course, it's smart and it's able to detect if there's a patch that got updated or got deleted. The system detects this and will reset all the files that it affected and rebuild the patches from scratch. This is also something that is done using Sentinel files. So final thing about this mix system is we have a lot of flexibility, but we have to be careful and we have to set the boundaries, because most of the things you're going to find in a repository is essentially files that are for the platform. It's not intended for the user to modify. So the user might accidentally modify them, and we make sure that the user knows about this by printing in red, again, on compilation, the sources that were changed, and to advise the user back to modifying only the files that we provide. So how to use it? Keeping track of platform and implementing over it is very hard, normally, in any kind of project. So what we propose is a standard Git forking solution. So if you want to use DIoT or use our build system, you just fork our repo and you work over it. And this, again, brings simplicity and doesn't increase the recursion of your project. And when it comes time for you, you're interested in a new feature that we added or some bug fixes, and you want to bring back the platform to the current version, you just have to rebase your code, your branch, in hours. And this is normally a good idea, because once again, we have a very clear separation between the code of the platform and the code of the user. So when you do rebase, I'll be very surprised if you encounter merge collisions. Of course, you cannot expect it to work from scratch. Maybe you need to modify one or two stuffs in these interface files, but in general, it will work. So that's all for me in the build system. We have a list of acknowledgements, which are all the colleagues that work in this ATS SoC workforce. And thank you very much. We are welcoming questions.
Thank you very much, guys. Your comments and questions? Go ahead.
Hi. There's a tool called HDL Make. Did you look into it? Is it the same? Is it inspired by it? Is there a difference?
So yeah, we looked into HDL Make, and it's actually something that one of our users already uses in their own implementation or of their own design based on the build system. From what I understand, HDL Make is more regarding packet managing. So since we are developing a platform design, we are not really relying on a lot of other tools. We are essentially the gateware and the packaging we have. It's very simple. It's just platform logic. So we do see some users using it, and of course, if there's a majority of them use, we of course will bring it to the reference design. But of course, in general, HDL Make, from what I understand again, is only a solution for gateware. We have to in this build system, we also are regarding the whole other part of the booting process of the SoC.
Very interesting talk. I'm interested to know how you're using the platform management unit for the platform management unit for monitoring the device remotely. The platform management unit, the PMU.
Yes. How we are using?
Yeah, like I'm curious. You access it remotely. Does it have its own Ethernet interface and everything? Or?
Okay. So currently we are using the one provided by Xilinx. But very soon, we have the implementation of remote console and remote resetting through a project that Irene is more familiar with, possibly?
Yes, but not extremely. So I'm not going to be able to give you all the details. And so if you want to know more, I can put you in contact with the developer. But indeed, the idea is to use the same network interface, but there are two queues. So that's what I remember and understood. So there are two queues, and we can use one of the two that is monitored directly from the platform management unit.
I guess they'll have different IP addresses for the system and the PMU?
So essentially, what is being implemented, from what I understand, is a lightweight IPMI sync. So that's the use, other than, of course, the normal SoC platform management. We also will add this part. So this is mostly requirements from the IT department and from the system managers.
So yes, the idea is to have IPMI tools accessible. So on the platform management unit, we have a firmware that is compatible with IPMI tools. So it's able to get IPMI commands from the network and deliver to this other queue, and then acts on this. But indeed, it's better to talk directly with the developer who is not in the room now. So if you're interested in too, so it's only a prototype so far. So it's working, it's being debugging. It's not released yet, but it's a very interesting development that should be presented soon.
Yeah, thank you. I'd be interested to speak with the developer.
Yeah.
So I'm curious about your continuous integration development. So it looks like that you have everything in the same repository, more or less, no? That both the gateware and the software, and you try to run everything. But for example, let's say that I don't change anything in the gateware, but you want just to do some modification in the software. You will have to rerun everything, or there is a way that you can pick up the oldest bit stream?
I think currently we do not have the hooks needed to realize if something is up to date or not. So I think currently it's rerun from scratch. That can be a very good improvement, because from versions to the others, we might only touch some parts of the software. But in reality, currently I don't think it's implemented.
Because yeah, we were thinking always for ROG, but there are Francesco, for example, is working with the Versal. And having similar things, so the idea would have like to have just special pipelines just for the software that takes, for example, the oldest available bit stream. In that way, you will save a lot of time. I don't know in your case how much you take to build the gateware, but every time, if it's not needed, especially with limited resources.
You're correct. Building, even though we are dealing with a platform design with not a lot of gateware already, we do have some platform management, some platform IPs. For example, we have a chip-to-chip already in the base design, which already takes a long time to compile. So yes, currently the pipelines take some time to finish.
Hello. I would like to ask if you do have a way of updating FPGAs only in your designs, or does every single FPGA update require a bootloader update in your workflow?
What do you exactly mean with FPGA update? You mean
I mean like bitstream or gateware updates, because like I come from a space background where we have very slow. Sorry, am I not? Do you not hear me?
Yeah.
Okay. So I come from a space segment background.
Okay.
And we have quite long or like quite slow uplinks to the satellite. So also we try to avoid bootloader updates in space whenever it's possible. So do you have similar problems? Do you also sometimes require to update the FPGA only without updating the bootloaders? Is that some consideration that you have, and do you have a workaround for this problem?
Okay, I guess this is more of a interesting question for the users, because as we stand, we don't have this kind of requirements. We don't have restrictions. In general, from what I understand from CERN, there's systems that all the systems here are easily accessible. So we don't have this problem of slow links. Everything is connected to the technical network, and it's accessible. So, of course, during runtime, while the machines are operating, in general, this is not touched. But, of course, there comes a time where these updates have to be done. And as so far, as we have on the IoT, if you really need to update the gateware without touching the software, you can, and you can rebuild the boot pin yourself. But it normally is not the best idea, because tied to your gateware, you have a device tree which tells the operating system what's really inside of your FPGA and your boards. And normally you have to update them hand in hand, or else you might run into problems.
Right, so essentially your solution would be to update the bootloaders if you would like to update the FPGA, right?
You could say.
Yeah, because that's where the FPGA bitstream is located, in the bootloaders. Okay, so as a result, basically the artifacts of your build, they do not contain like the FPGA bitstream itself, but rather the whole package along with all the rest of the bootloaders generated by the bootgen utility from Xilinx.
Yes, so all of those, the ARM Trust firmware, the device tree, the gateware, PMU, FSPL, and U-boot. FSPL is the first stage bootloader. All of them are inside of the boot pin, which is the final outcome of this build system. So everything's packaged there, and that's the way that Xilinx works.
Yeah, okay, thanks.
No worries.
But I wouldn't exclude in future that this might change, because
yes.
We know that it's possible to reprogram the FPGA. So if a new bitstream, so maybe there is Alan that also is working on the IoT. If you can.
Hey. Okay. Yeah, the day of today, you get the artifacts, you get all the binaries that are generated. Also the bit string, and it could be possible that you can load only the bit string or Linux without the update of the rest of the binaries.
So the idea is more about how so one of the things that will be looked into is these tools for providing updates to the software and to the gateware. So I can see how a new bit stream could be uploaded, like through the network, distributed to the device, and then reprogrammed to the device. But then, of course, there is the problem of being sure that device tree is still compliant with your bit stream. So it's a risk to be taken.
Yeah, thanks. We have a way internally of uploading the FPGA like individually without the rest of the bootloaders, as this is quite important in our segment. So yeah, thanks.
Yes, thanks.
Let's go for one last question.
There's a question from outside. and they are asking why Yocto recipes and build system couldn't be used into DI/OT. Why Yocto recipes and build system, Yocto? Do you know what? Yeah.
So maybe I can
so that's the
reply.
yeah,
yes. So indeed, the idea is to have exactly the same distribution that we have on the front-end computers. So to treat a system on chips as we treat other front-ends in the accelerator, so that we can use the same tools, and they are managed centrally. So when we look at the separate projects, what they were building on their own, you could have all sorts of solutions, but then we try to standardize, and then the idea is to have, we have one team that is taking care of the OS for the accelerator, and for them it's easier to have a single distribution to maintain. And then what is just different for SoCs is the kernel, since they're taking the Xilinx kernel. So this was the strategic decision.
Okay, thank you.
Thank you very much. Thank you very much, guys.